All right, welcome back. This is an ALEKS topic that's called calculating vapor pressure from boiling point and enthalpy. And this is a pretty good little topic. It's fairly straightforward. We're going to need to use this Clausius-Clapeyron equation. There's a few little conceptual things that we want to touch on before we leave. So for this problem, I guess the key is to take this concept of the normal boiling point and relate that to a vapor pressure. So the definition of a boiling point is when the vapor pressure is going to equal atmospheric pressure. So when it tells us that the normal boiling point is 133 degrees Celsius, it's actually telling us that the vapor pressure at that temperature is 1 atmosphere. So like I said, the boiling point is going to be where the vapor pressure is equal to the atmospheric pressure. The normal boiling point is the boiling point under normal conditions, which would be 1 atmosphere. So this temperature of 133 degrees Celsius, that's telling us that the vapor pressure at that temperature, vapor pressure will equal 1 atmosphere. And that's sort of a key piece of information that we're going to need to have in order to plug that information into this Clausius-Clapeyron equation. The other point that is sort of a common mistake is that this delta H of vaporization, we want to convert from kilojoules into joules. So the units on R are joules over Kelvin times mole. So since our R value equals 8.314 joules over Kelvin times moles, we want to make sure that our delta H of vaporization is also in terms of joules, right? So this would be joules over moles. So we want to have our units be consistent here. So when I am going to solve this, I'm going to take the information up here, and I think it's nice to just organize your information. I'm going to say that P1 is the vapor pressure that I'm looking for. That means that T1 needs to be the minus 29 degrees Celsius, which is 244.15 Kelvin. And then P2, that's going to be my 1 atmosphere, right? That's the known information, and then from the boiling point. And then our T2 is going to be our boiling point, 133 degrees Celsius, which is 406.15 Kelvin. So now it's basically just plug all this information in and figure out what the answer is. Solving this is a little confusing, so I'm going to run through that real quick over here. So writing everything out, natural log of P1, and I chose P1 to be my my unknown, just because it's on the top. It makes solving this a little bit easier. It saves one step at the end, I guess. Delta H vaporization, R value, 1 over T2. Now be really careful about being consistent with T1, T2, P1, P2. We want to make sure that this is P2, that correlates with this T2. And then our other T1, 244.15. We do need to convert these into Kelvin, just because of our units, and also that's because that's how it works, I guess. Now we're going to go ahead and solve this. So if you sort of calculate this out, again, be careful with how you're entering everything into your calculator. You should end up with minus 2.947 for the right-hand side. And then we still have the natural log of P1 over 1, or we could just sort of simplify that, right, to just P1. And then to get rid of the natural log, we're going to take e to the power of both sides. So that gets rid of the natural log, and then we would end up with P1 over 1 atmosphere equals 0.052. But obviously, this we could also just rewrite that as P1 equals 0.052 because times 1 atmosphere. So our final answer here, P1 equals 0.052 atmospheres. That's what we're looking for. Hopefully that explains all of this topic and how you're going to use the Clausius-Clapeyron equation. It does not matter which, P1, P2, T1, T2, if you switch these. So if you switch these, so you've got 1 over P1, and then you switch these, it doesn't matter. So I arbitrarily decided, how I was going to set that up, but it really doesn't matter how you do it. It should all still work out. All right.